Hello physics students. In this topic, we're going to be studying waves. But waves are caused by vibrations. So before we study waves, we're first going to have to learn about vibrations. In particular, today we're going to be studying one special kind of vibration called simple harmonic motion. Let me show you an example. What I obviously have here is a car on a track, but you may not be able to see this in the camera view, but there are two springs on either side of this car, and what this achieves is that when I pull this way, this spring stretches and it pulls back the car to this point where the springs are in equilibrium, and when I go this way, it pulls it back the other way to back to the equilibrium. And this, I can achieve simple harmonic motion in this setup by simply pulling the car back like this and letting it go. And what you see, that's simple harmonic motion. It's a smooth vibration. Notice the car goes back and forth nice and smoothly. It doesn't do any kind of like jittery motion, which is also a vibration, but not a simple harmonic motion. Now, so the first way I achieve this is I pulled this back and let it go like that. So that's one way. Another way I could achieve simple harmonic motion with such a setup is I could take this in its equilibrium position and give it a brief shove and then create the simple harmonic motion that way. Or I could even do a combination of the two. I could pull this back away from this equilibrium point and shove it also. All of those are simple harmonic motion, just beginning at what we call different initial conditions. All right, so the topic for today is simple harmonic motion. Sometimes we abbreviate that SHM. By the way, things that vibrate according to simple harmonic motion, we sometimes call them simple harmonic oscillators. We abbreviate that SHO. So one possible cause, as we saw in the demonstration, is a spring. And a spring has a force, F equals kx. That's from the reference table. You could look it up in the mechanics section. But I added a minus sign. And the reason why I put the minus sign is because if I displace an object in simple harmonic motion to the right, maybe we'll call this in the positive direction, the force is in the opposite way of the displacement. So if x was positive, the force was negative. And if I displace this oscillator to the left, maybe we call that negative displacement, the force is back to the equilibrium the opposite way. So displacement, force, always opposite, so we put that minus there. Not really critical for our course, but if you study physics in college, that would be more essential. So I've diagrammed what we've had in the demonstration. We've got an oscillator on a spring. Now I had two springs, but you could have a spring that either stretches or compresses. So that's what this spring is. It's kind of open coiled and it could go either way. But this is the spring in its relaxed position. It's here. We define this point as x equals 0. And then what I do is I pull this to the right and I released it. And right on if this were like an x-axis, we typically call right positive. So I displaced this some amount of x. We're going to call it positive A for now. I'll explain in a little bit what that means. And I let it go, and then it shoots past equilibrium and overshoots, and this time compresses the spring and gets it ready to be propelled the opposite way. And it goes exactly the same distance to the left of equilibrium. So we say this is at x equals 0, x equals negative a this time. And so this thing oscillates between these two extremes around the x equals 0, between x equals plus a and x equals minus a. Let me create a pause to give you a chance to copy all this down. All right, so a mass on a spring is only one possibility. You could have other objects oscillating for different reasons that are also in simple harmonic motion. So simple harmonic motion is more general than just a mass on a spring. In general, a simple harmonic oscillator is something that traces out a smooth curve like this if we were to plot x as a function of time. Remember, this is oscillating back and forth, starts at some positive value, goes to 0, and then to the negative, and then goes back to the positive. So this is like how far it's moving along the x-axis or the displacement. You might notice and recognize this shape. It is the cosine function. So you could write this down, but it's not part of the curriculum. But this would be the equation of this particular oscillator. And of course, this repeats, so I try to draw a lighter line. But this keeps going indefinitely. If there's no friction, it'll keep oscillating. But of course, or I shouldn't say of course, but another possibility is that it could oscillate as a sine function or any kind of sine-cosine combination, but that's beyond the course curriculum. But the point is, you see that smooth vibration. Now, there's some things that we define about simple harmonic oscillators. The concept of a cycle. A cycle is one complete vibration. What I have darkened here, or really bold, that's one cycle. It's what repeats itself over and over again. So we have one cycle, then we'd have a second cycle, and then a third, on and on. It's the smallest part of the motion that repeats indefinitely. That's a cycle. Then there's what we call amplitude. I already kind of, sort of hinted at it. The symbol A is what we use for things in simple harmonic motion, and it's measured in meters. And what it is it's the distance from equilibrium to the point of furthest displacement. So, like for example, from here to here is the amplitude, or from here to here is the amplitude, or from here to there is the amplitude. It's basically 1/2 the total motion back and forth. It's only half of that is the amplitude. A couple more terms. Let me make some room. Amplitude, next term, period. The symbol we use for it is capital T. We already saw this when we were studying orbits, or when we were doing circular motion. When things went around again and again, we don't use a lowercase t, we use the capital T. Well, this isn't going around in a circle, it's going back and forth, but it's the same idea. It's something that repeats over and over, and in physics, when something repeats over and over, we don't use lowercase t for the time. It's a capital T, and it's measured in seconds. And what it is the time for one complete vibration in seconds is the period. And then one final term, frequency. Let me write what it is. So it's the number of vibrations in 1 second. Now, there's a relationship between these two. Let me just say also it's measured in hertz, but another unit is vibrations per second, or 1/seconds. So, like for example, one example could be 1 hertz. That would be 1 vibration every single second. 2 hertz is 2 vibrations in 1 second. 3 hertz is 3 vibrations in 1 second. 4 hertz is 4 vibrations in 1 second. You get the idea. The tuning forks, something I'm going to show you later, never mind. So I was getting ahead of myself. So number of vibrations per second. But there's a relationship between these two. Because think about this. If I told you something had a frequency of 2 hertz, in other words, in 1 second, it went twice, then how long does it take for just 1 vibration? If it goes twice in 1 second, what's the vibrational period? You may have seen it, it's 0.5 seconds, right? If that's 1 second, then just one of them is half of a second. If I had a frequency of 3 hertz, 3 vibrations in 1 second, what's the time for one? Well, if there are 3 of them in 1 second, each one must be 1/3 of a second. And so the relationship between these two variables is that the period is the reciprocal of the frequency. This formula is actually on the reference table. we're in a new section here on page 5, and you see the wave section here. Right here is this formula that I just wrote on the board, T equals 1 over F. Period is 1 over the frequency. All right, so let me create a pause to give you a chance to copy these notes down. Okay, so the next thing that I'm going to do is I'm going to reconfigure the camera, and I'm going to show you these concepts demonstrated out on the harmonic oscillator that I showed you earlier. The first thing that I'm going to do is use this harmonic oscillator to demonstrate what a cycle is, because very often students use the concept incorrectly, particularly when they have to count cycles or count vibrations. Let me show you the incorrect way to count cycles or vibrations of this oscillator. If I were to go like this and go 1, 2, 3, 4, 5, 6, 7. A lot of students do that, and that's incorrect. They think a cycle is this. Here's another cycle. But that's not what repeats it over and over again throughout the motion. The car doesn't always just move to the left. It doesn't move this way and then disappear and reappear here and always just move to this direction. It goes back and forth. So this is the correct way to count off cycles as this thing is vibrating. I let it go. 1, 2, 3, 4, 5. In other words, a complete back and forth. The next concept that I want to demonstrate is amplitude, because that also is something that students apply incorrectly. So what I'm going to do is put this bar right here at the center of the car. When it's in equilibrium, this is what we define as x equals 0. Now, if I stretch this oscillator like this and I let it go from here, it'll obviously overshoot and come all the way over here. So a lot of students think that the amplitude is from here to there. In other words, the whole range of motion of the car. Not correct. Amplitude is from equilibrium to one extreme, that distance, or you could measure from equilibrium to this extreme, this distance. They're the same. In other words, it's 1/2 the total motion of the car is the amplitude. The next concept that I want to demonstrate is period, which I talked about already. It's the time for one complete vibration or one complete cycle. So this is how I would correctly measure the period. As this is oscillating, I would start it when it's here and stop it when it returns. So I'd go like this, start, stop. And you see that when it was here, I hit the start button, it came back, and I hit the stop button. And I get about 1.08 seconds is the period of oscillation for this car. All right, so let me go back to the board and continue with our notes. Now, I just showed you how you could measure the period of an oscillator using a stopwatch. But it turns out that for some harmonic oscillators, there are actually formulas that you can use to calculate the period without actually seeing it move. So I'm going to show you the concepts behind the formula first before I show you the formula. But let me reconfigure the camera so we could see the patterns, what affects the period of a mass on a spring. So there are two main factors that affect the period of oscillation of a harmonic oscillator. One is the mass. Notice this, when I let this go, I have a certain period. Start, stop, start, stop. So that period gives, you get a sense of that period from even hearing the rhythm of my voice. I'm going to add more mass to this car, some steel blocks here. And when I go like this, and I go start, stop. Takes a lot longer. In fact, if I were to time this, start, stop. About 2.8 seconds, as you could see. And then if I were to time this like this, so start, stop. 1.33 seconds. So more mass, more period. Another interesting thing that is not in the formula, before I move on to the second factor, is the amplitude. A lot of students would say that this takes longer to oscillate than that does, because the other one went further. And it's not true. If you were to do this multiple times and time this, I got about 2.64. If I do it for a small oscillation, 2.63. So it comes out to be about the same period for a small oscillation as a large one, counterintuitive. So only mass so far, more mass, more period. The next factor that we're going to look at is the spring constant. So you see these springs, they're very loose over here, and you could even see the coils are very thin, and this car has a certain period of oscillation. Over here, you already saw this earlier, with this car in the view, that this car has, it's made with a spring. The oscillator is made with a spring with much thicker coils, so it's a tighter spring. We would say that this, physics-wise, has a higher spring constant K than this spring over here. And if I pull these back at the same, and let them go at the same time, you see this one goes much more rapidly. So this basically here, with a bigger spring constant, has a smaller period. So more mass, more period, more spring constant, less period. So you could already get a sense of the formula having to have a numerator and a denominator. So let me go to the board and I'll show you the actual formula that has these patterns in it. So the period formula for a mass on a spring is right here. T equals 2 pi, this is 3.14, square root of mass m in kilograms over spring constant newtons per meter. This formula shows the patterns we saw. First of all, there's no amplitude in the formula, so small oscillations, big oscillations, same period. And then more mass, more period. That's why mass is in the in the numerator here. And the tighter the spring, the more spring constant, the faster that went, the less the period was, so we put spring constant in the denominator, so the bigger it gets, the smaller that gets. And I want to have you have this in your notes also, the reminder of the spring force, what spring constant is. More spring constant, more force for the same spring displacement. Now, it turns out that there's another kind of oscillator that's very popular to study in high school physics classes, and that's the pendulum. You've probably heard of the pendulum. Actually, we studied the pendulum earlier in the year when we were studying energy. And pendulums also have periods. And we could see the patterns here because I have 3 pendulums here, masses at the end of long strings, that will demonstrate the patterns of the period of a pendulum formula. So first thing, I have one pendulum here made of lead and the other one made of wood. And you would think that they would have different periods because the mass is different, like we saw in this formula, but it turns out that it's not true. If I pull these back to the same distance and let them go, they oscillate pretty much at the same frequency, same period. They're not together because I'm not really letting them go together. But basically here, this is a little bit better. Same period, even though the masses are different. But what I have here is another lead pendulum. And now, notice the string here is much shorter. And that's the effect that affects the period. Notice if I were to time this start, stop. So start, stop. That's one period. If I time this one, I would go start, stop. So this, with a longer string, has a greater period. The formula that shows that pattern is right here, 2 pi square root, length of the pendulum in meters right here under the square root in the numerator, so more length, more period, and then G 9.8 in the bottom, also under the radical, even though that's not quite clear there. Let me just extend that radical a little bit. Again, notice no mass in here, it does not affect it, and also no amplitude, but there's a little sort of caveat, we say, that this formula is only valid for relatively small oscillations. If you go like this, that formula is no longer accurate. For the reason for that is that this is has complexities in it, the pendulum, that's beyond the scope of the course. But just know that when we use that formula, we have to have relatively small oscillations for it to be valid. All right, so let me create a pause to give you a chance to copy these notes down. All right, before I move on, I just want to point out that this formula is actually not on the reference table because neither of these are, because they're not actually part of the Regents curriculum. I just included them today because we're going to be doing a lab on simple harmonic motion, so you need those formulas to be able to do the lab. Okay, so next thing. There's one more big concept for today, and I don't want to just tell you about it. What I want to do is show you the concept because I find it very interesting, kind of fascinating to watch. I'm going to show it to you in a demonstration, so just give me a moment to, again, reconfigure the camera. When I set this into motion earlier, what I did is I gave the car one single application of energy. Energy, yes, I put in a force time distance. I did work on this car, and then I let it go, and then that energy that I put in with my muscles became like a vibrational energy. And this car vibrates at some period and some frequency, like naturally it just vibrates at that frequency. So the frequency at which it vibrates when it gets such an application of energy and released is what we call a natural frequency. So this has one natural frequency, we could observe it there, and this has another natural frequency, we could observe it there. But the truth is, I could get this to vibrate at any frequency that I want. I could take my hand and just go slow like this, and I'm making pretty close to simple harmonic motion, but different than the natural frequency. Or I could apply over here at the end of the spring, which is a little bit out of camera view, but I could make any frequency of vibration that I want. But what we're going to see is that the response of this is greatest when I match the natural frequency. For example, if I go over here and I go fast my hand like this, notice the car is just kind of wiggling around. It's not really responding much. But now let me go and match the frequency, the natural frequency. See that frequency? I'm going to match that with the spring over here. And what you could see is that the car is really moving dramatically. And we could say that essentially I broke the oscillator. The spring came unhooked here. Now, if I wanted to unhook the spring with one single application of energy, I'd have to drag this all the way here, and it'd be a lot of force to get it to push it and get it to pop off the spring holding there. But what I did instead is I was vibrating at the natural frequency, and every time I was just adding a little bit more energy to the oscillations. And that made the amplitude build up more and more and more to the point where I overwhelmed the structural integrity of the oscillator. So that's what we call resonance. When that happens, when I match the natural frequency and then the thing responds by really oscillating quite dramatically, it's called resonance. I could achieve resonance with this oscillator, but look here, when I did the resonance here, see the rhythm of my hand vibration? Slow. If I try that over here, it's not going to work. It's not going to make this resonate because I have to match this car's natural frequency. So I have to go like this with my hand. And let's see what happens when I do that to this car. And there, again, I broke the structure. I broke the oscillator by just simply repeating a vibration. So resonance in structures is often a bad thing. I'll talk more about that. But let's go back to the notes, the board to summarize with some notes. So natural frequency, the frequency an object vibrates at after receiving a short burst of energy. Like when I shoved the car and then it just oscillated all on its own. And then resonance, the condition that arises when an object is stimulated by a vibration with a frequency equal to its natural frequency. So when I took the car and I shook it like this, the spring, the car didn't respond much, but when I hit the right rhythm, boy, that car really started to oscillate, and then eventually the springs let loose. So let me create a pause to give you a chance to copy these notes down. All right, well, I have some other really interesting, really cool demonstrations that I'm going to show you. So let me reconfigure the camera, show you some more examples of resonance. So what I have here are a couple tuning forks. Tuning forks are metal like this, forks of metal that are manufactured and machined to vibrate at a certain particular frequency. This has a stamp on it. You probably can't see it. It says 256 C, which is the musical note middle C on the piano. They are used actually to tune instruments. So that's why they're called tuning forks. They're mounted on these wooden boxes to amplify the vibrations of the metal and therefore create audible sound that you can easily hear. And so what I'm going to do is strike this one time, giving it one burst of energy, and then it'll vibrate according to its natural frequency of 256 hertz, and you'll be able to hear it. So, and then notice when I put my hand on it, it stops the vibrations, the sound goes out. So I turn the sound on, and then I turn it off. Once again. Right? This is another resonance box tuning fork, and it's made to make the same exact note. Turn it on, turn it off. Now I'm going to demonstrate the principle of resonance. Very interesting. Watch what's going to happen. I'm going to hit this tuning fork, and then I'm going to stop it. And this one is vibrating even though I never hit it. Watch again. I'll hit, and that one's vibrating. Or I could go the other way. So the reason why this happened, again, these vibrate at the same natural frequency, 256 hertz. When this sets the air to vibrate, the air molecules hit this at the right rhythm, and then that rhythm builds up. That's called resonance, and then we hear the sound. But the nice thing about this has some adjustments. I could move these and I can make a different musical note. And you'll be able to hear that it is a different note when I strike. So this is the original note, and now different note, higher, right? So let's see if resonance works now. Not really, okay? A little bit. Maybe we'll change it a little bit more. Or maybe, let's try here. Yeah, it doesn't really work. Now, I cannot pass the vibrations back and forth because I'm making this oscillate at the wrong frequency, not at the natural frequency, so the oscillations don't build up. I could also create resonance with wine glasses. You've probably seen something like this before. So what I can do is hear the natural frequency by just giving this a single burst of energy, and that's the natural frequency of this glass, that's the natural frequency of this glass, and that's the natural frequency of this glass. Now, if I were a trained opera singer, which I'm not, I could go listen to this and then stop it and sing that exact same note. And if I don't match the exact same note, the glass will not vibrate. But because I would be a trained opera singer, I could hit it exactly. And then this glass would start resonating, and I'm holding that note and singing and letting the vibrations build up, and eventually I could shatter the glass. A good opera singer can shatter glasses through singing the exact note with a good intensity and create resonance and get the glass to shatter. But I could also create resonance without singing by doing this little thing you've probably seen. Rubbing my finger along the top of the rim. And now I'm creating resonance by a similar effect to when you pull a string across a violin. It's that same kind of interaction, generating vibrations through rubbing. This one, we could hear the same note resonate through the rubbing. And here, same note. Okay, so resonance, different natural frequencies, different resonant frequency, or the same resonant as the naturals of each of the glasses. So breaking a spring oscillator, shattering a wine glass when singing. Resonance, as I already said, can be a destructive force, can actually break structures. And one of the most dramatic examples of that is actually film footage. It was caught on video, a bridge actually collapsing because of resonance. So that's what I'm going to show you now, some old video clips back from the 1940s when the resonant effects of the wind blowing on a suspension bridge caused oscillations that ultimately caused the whole bridge to rip itself apart. So let me get this playing and I'll turn out the lights so hopefully the view on the projector screen will be better with the camera. So the Tacoma Narrows Bridge in California opened on July 1st, 1940. Just 4 months later, it had collapsed. Right from the start, the bridge showed signs of being problematic. Notice the bouncing. In fact, many people refused to drive over it. Engineers continued to observe the bridge to try to get a better understanding of what was going on. Then came the wind of November 7th. As you can see, it wasn't extreme, but it was significant. Even in the morning, the bridge already showed signs of excessive vibration. Look at the movement of this truck crossing. And then the motion rapidly escalated. From then on, crossing it became impossible. If you look at the nearest part of the bridge when it reaches its peak, you could gauge the size of the steel beam by comparing its thickness to the light poles whipping about on the roadway. From this view, the beams look like they're made of rubber, but they're actually 8-foot tall steel beams. In this view, you could see a man walking, for some reason very casually along the roadway, and then he just sits down on the curb. I think you can see the man again in this view, trying to walk back to the car, but he's stuck just straddling the median. This is a closer view of the car. The man was trying to get back to the car because his daughter's dog was trapped in it. And then finally, the vibrations got so big, they broke the concrete and tore the steel beams. The center has fallen away, but more pieces continued to fall for some time. Here's a view of the side span shaking violently as more pieces fall off. Here's another man running to safety. And as you can see, the bridge is destroyed. Destroyed not by a hurricane or a tornado, but by moderate wind and resonance. No person died in the collapse, but the dog in the car unfortunately did not make it. So very dramatic, as I said, tragic example of how resonance, the wind blowing at the right frequency, caused vibrations that kept building and building until the bridge made of 8-foot thick I-beams and concrete and giant steel cables ripped apart because of the pulsating that was the pulsing energy that was received in the right frequency. So one other example that I looked up, you may have heard this, I don't know if you've heard this, but when soldiers march, they all march in unison, discipline, you know, stomping together. But when they reach a bridge, they don't march across the bridge. I guess there was all the way back in 1831, there was a case where the British military was marching soldiers across a bridge, and that marching in unison caused that similar effect, and they matched the natural frequency of the bridge, and then the vibrations made the bridge collapse, and people got hurt in that situation. So they don't march because they don't want to give that stimulating energy at the right frequency to cause resonance. All right, so that's it for today for simple harmonic motion. A lot of information, a lot of demonstrations. So what I want to do is just sort of wrap it together and tell you what you should really study for the Regents. What you want to know is all the definitions that I put on the board, what a cycle is, what an amplitude is, what a period is, what frequency is, the relationship between period and frequency. Those are really key to understanding the Regents or doing well on Regents for vibration questions. And also the concept of resonance is pretty popular, but just the concept, not much to calculate there. The formulas that I put for period, again, those are not part of the curriculum. You'll need them for the homework and for a lab, but not for the Regents. So go back and just look over those notes and make sure you're familiar with those and you have those concepts committed to your memory. All right, so I hope you enjoyed the video. I hope you enjoyed the physics. I'll see you in the next physics video.